So in this video, we are going to talk about reactions of a carboxylic acid derivative called an ester. So specifically, reactions of esters. So esters react with nucleophiles, just like any other carbonyl compound. However, they're sort of like in the middle of the road in terms of reactivity. They're not the quickest to react. They're certainly not the slowest. And we have a couple of ways that we can sort of help things along a little bit. We can do these reactions under the catalysis of an acid. So we can have acid catalyzed reactions. So in this particular instance, we should note that in an acidic solution, all organic intermediates are going to be positively charged or protonated, right? Should say positively charged is probably better. All organic intermediates are either positively charged or they can be neutral. We could have a base promoted. So notice there's a difference there. And when we go through the specific examples, I will make sure to let you know why we use a different word. This is not catalyzed. It's just promoted by the use of a base. So like encouraged by the base, right? And in this instance, all organic intermediates are either going to be negatively charged or neutral. I'll just abbreviate that to save some time. So they're either negatively charged or neutral. In this course, we're specifically going to focus on the reaction of an ester with an alcohol, or I'm sorry, with water to give a carboxylic acid. So we're going to focus in this course on the hydrolysis, in other words, of an ester. So specifically in this course, we're going to react the ester with water to form the carboxylic acid. And the name in general of this type of a reaction is a hydrolysis. We're going to break down one molecule into two molecules using water. Lysis is just to break apart. Hydro refers to the water. So we're going to slice up the ester using water, essentially. So this can be done under acidic conditions. So we'll catalyze the reaction with acid. Remember a catalyst. So from Gen Chem, remember a catalyst is something that you actually have to regenerate at the end of the reaction. We'll do this under acid catalysis or base promoted conditions. So the base in this instance is going to end up encouraging the reaction by increasing the rate of the formation of the tetrahedral intermediate that we talked about in the previous videos, where, you know, these reactions have a typical pattern. The way they react, the carbonyl gets hit, a tetrahedral intermediate is formed. It's not stable, it collapses, something leaves, kind of a thing, right? So the base is basically going to promote that piece of the reaction that is slow by being a better nucleophile than water, right? So under acid catalyzed conditions, water is going to be the nucleophile, but we're going to activate the carbonyl toward nucleophilic attack. Under basic conditions, the base will be the nucleophile. And because negatively charged species are better nucleophiles than neutral ones, the base is going to promote the reaction by being the better nucleophile. The base is consumed. So the base we're going to use is hydroxide, OH minus. That'll be consumed by the reaction, not technically a catalyst, therefore, right? Because it's not generated back again at the end. And then there's this like sort of in-between reaction where we can have an ester react with an alcohol with the help of an acid catalyst. So I'll put that into that category as well. And the name of that reaction is a transesterification. So you're essentially getting another ester out of the mix. You'll start with one ester, react it with an alcohol, end up with a different ester, right? So transesterification will be sort of like a little offshoot of our acid catalyzed hydrolysis reactions. So let's just start with the acid catalyzed reactions. And we'll tell you why we're using an acid and what it does. So we're basically going to take an ester, and I'll just take some generic ester. So we'll just use R. We have our carbonyl. O, and then we'll let this be different. So R prime, that's all that means. The little prime just means it's a different group, right? We're going to subject this ester to an acidic solution, so essentially H3O plus, right? Usually we just put H plus, but I think it's nice to actually draw this out so that you don't wonder later on where the water came from, right? So this is protonated water, right? The hydronium ion. And this comes from mixing an acid or dissolving an acid in water. So the first thing that happens is your carbonyl is going to be activated, right? We're going to protonate the carbonyl, and that is going to encourage the carbon to undergo nucleophilic attack. So now we have an activated carbonyl, or in other words, we have an activated ester in this case. And the water now can come in as a nucleophile and attack that carbon. So it was partially positive before, but now when you attack it, we can release electron density to the oxygen that has an actual positive charge. And what you form is your first tetrahedral intermediate. So here I have this. I have my OR, part of the ester, and then this is from the water that attacked. I'm going to draw that rather suggestively. We'll have a positive charge here. So this is our first tetrahedral intermediate. In this particular case, I'm just going to highlight this and give it a little number because we'll talk about these. So up here, I'm just going to say, let this be tetrahedral intermediate number 1. This is done under aqueous conditions, right? Because it's acid catalyzed. So what you have is some more water that can come in and take that hydrogen away, return electron density to the oxygen. This is in equilibrium with your neutral tetrahedral intermediate. I'll re-explain all these steps after. I just want to get them drawn out for you. So here we have our neutral tetrahedral intermediate. I'm going to circle this and say, let this be number 2. This will denumbering these will make it easier to look at the pattern. This little pattern pops up time and again with these particular molecules. So our neutral tetrahedral intermediate can then be protonated. And this will come from some more of that acid, or the hydronium ion, in other words. And you get a third tetrahedral intermediate, which is also protonated. I'm going to put that down here. So we're going to get our carbon, our sp3 now hybridized carbon, positive charge on that oxygen. So I'm going to circle this because we'll refer to this again as well. This will be tetrahedral intermediate number 3, which is also protonated. So we're going to highlight these. Our first tetrahedral intermediate is protonated. Our second one is neutral. And our third one is protonated. The electrons, and of course you can pick whichever hydroxyl group you want, because this tetrahedral intermediate is not stable, we have a carbon that's bonded to, in this case, 3 oxygens, but a carbon that's bonded to at least 2 oxygens, and that tetrahedron is not going to be stable. Pi bond is going to reform, and we can kick off the alcohol. And what you get is your carbonyl back again. Draw that just a little bit more suggestively because we're going to be taking that off. Move the hydroxyl group up there. And then this alcohol that we kicked off, R prime OH. Water can come in. Grab that hydrogen. Notice how we're regenerating our acid catalyst. And the product of this reaction is going to be a carboxylic acid and an alcohol. If you're curious, since you're staring at all of these different types, all of these reaction arrows that show an equilibrium between each of these products or these intermediates, right? This whole entire reaction is reversible. So you could take a carboxylic acid and an alcohol and an acid catalyst, and you could cook it up. Sometimes this reaction happens at room temperature, and you could make an ester. In fact, the Fischer esterification reaction is an example of that, which we'll go through this again and do it all backwards when we talk about reactions of carboxylic acids. So what's actually happening in this particular reaction? Well, what we believe might be happening is the carbonyl gets protonated, activating it toward nucleophilic attack. The tetrahedral intermediate is formed. So tetrahedral intermediate number 1 is formed. And it is in equilibrium with its non-protonated form. So anything in solution that is capable of removing a proton will deprotonate that tetrahedral intermediate. We get the neutral tetrahedral intermediate, the non-protonated form, can be reprotonated on either the hydroxyl group, so one of those OHs, or the alkoxy group, the one that I chose to protonate, right? If the hydroxyl group is protonated, water will leave and the tetrahedral intermediate collapses. Or I should say when the tetrahedral intermediate collapses. If the alkoxy group is protonated, then an alcohol will leave when the tetrahedral intermediate collapses. Here's the thing. I drew it one way. It is possible it could happen the other way. So since water and alcohols have similar basicity, right? They have similar pKa values. Either option is probable. The acid will catalyze the entire process by increasing the reactivity of the carbonyl and by increasing the leaving propensity of the leaving group, right? Because we're using it there too to create that good leaving group, right? The alcohol. Since tetrahedral intermediates 1 and 3 are equally likely to collapse, both the ester and the carboxylic acid are going to be present at equilibrium. This is where we're going to go back to Gen Chem and be like, okay, it is possible that 1 and 3 are equally likely to collapse, and so therefore this reaction could go forward or backward. At equilibrium, in other words, both of those are going to be present. If you decide you want to force this reaction to the right, you can lean on Le Chatelier's principle and use excess water, which is not hard to do because you just use it as a solvent, right? If you use excess water, that's one of the reactants. So if you get this thing to equilibrium and you use excess water, you can force the equilibrium to the right by Le Chatelier's principle, or also by Le Chatelier's principle. If the boiling point of the product alcohol, this thing right here, if the boiling point of this is significantly lower than the other reaction components, so if the boiling point of this is significantly lower than that of other reaction components, it can be removed by distillation. So you get a system at equilibrium, and you're going to disrupt it, either by adding excess water. So if this is used in excess, or if you know the boiling point of your product alcohol and it's lower by a decent amount than other reaction components, you can get rid of that by distillation. Adding an excess of reactant or selectively removing one of the products will push equilibrium in the forward direction by Le Chatelier's principle. So we can sort of set this up so that we force the hydrolysis of the ester. And you could do the same exact thing if you're trying to make the ester from the carboxylic acid or the alcohol. So we can selectively either remove something or use, usually in that case, the Fischer esterification, you'll use an excess of the alcohol. It's just easier. But either way, you can encourage this reaction to go in the forward direction if you have a better understanding about what might be happening in the pot, right? So let's just take a little second here and pause and realize what's actually happening. Remember those 3 tetrahedral intermediates that we talked about in this reaction? So I numbered them 1, 2, and 3. We have a protonated tetrahedral intermediate, number 1, a neutral tetrahedral intermediate, number 2, and then a protonated tetrahedral intermediate, number 3. You are going to notice this pattern occurring for other carboxylic acid derivatives. So other acid, I should say, catalyzed reactions. So let's just note this. There's a pattern to the reactivity in an acid catalyzed reaction. You're going to form your protonated tetrahedral intermediate. I'm going to just abbreviate these. Number 1, it will be in equilibrium with the non-protonated or the neutral tetrahedral intermediate number 2, which will be in equilibrium with the protonated tetrahedral intermediate number 3. This pattern, again, is going to repeat in a lot of other acid catalyzed reactions. So you will notice this happening. If it helps you to think through the mechanism, or I should say proposed mechanism, it also helps to lean a little bit, like we said, on the Gen Chem stuff, right? Because all of these are in equilibrium, all of these steps. So in order to encourage this to go in the forward direction, we can use Le Chatelier's principle and sort of modify our reaction conditions in our favor. You could remove product, or you could add reactant and tip the scales in your favor. I want to show you one other example of acid catalyzed reaction for an ester. So here we were doing a hydrolysis reaction, right? We're breaking the ester up using water. So lysis means to break up or to slice. Sometimes it's easier to remember. And we're using water essentially to do it, and a little acid catalyst. There's another type, a specific type of acid catalyzed reaction. It's where an ester is going to react with an alcohol instead of water. You'll get another ester. So we call this a trans esterification reaction. So here we'll have an ester reacting with an alcohol instead of water. So that'll be your nucleophile. With the help of an acid catalyst. So for example, we could take, I'll call this side R because it's not really like the star of the show. And we'll make a specific ester just on this side. Mostly because the alcohol we're going to introduce is going to cause us to create, this is going to be under acidic conditions. We're going to protonate the carbonyl. The whole mechanism, right, is going to follow the same as the hydrolysis reaction. We're going to protonate the carbonyl oxygen. It's going to make that carbon hotter for nucleophilic attack. Then your nucleophile comes in. In this case, we could just use a different type of alcohol to show that all you're going to do is get a different ester. So we could use, say, benzyl alcohol. And we're going to use this in excess. So this is going to encourage the forward process, right? By Le Chatelier's principle, because this is going to follow a similar reaction mechanism. You protonate the carbonyl, of the original ester using our acid catalyst. So this right here is going to be our acid catalyst. If you ever see an arrow like that, that's telling you that at equilibrium, your products are favored, not your reactants. We'll have our R group, whatever it was, that stays the same. After all those same steps that we just went through, we'll have our carbonyl. And now we have a different alkyl group attached to the carbonyl, thanks to the other alcohol that we just used, our nucleophile. So instead of breaking down the ester using water, we're going to break down that ester using an alcohol just to make another type of ester. And the alcohol that actually comes off if possible, can be distilled to remove, if possible. You know, if all these things boil within like 1 or 2 degrees of each other, that's going to be kind of a drag. You know, even fractional distillation is going to be iffy on that. You might get some mixed stuff. But if you've got a good, you know, decent, say 10-degree difference in boiling points, then you can set this thing up to distill your product alcohol and remove product while using an excess of reactant to really shove this thing in the direction of the formation of your new ester. So this, again, will follow the same mechanism as the hydrolysis. You'll use an excess of your nucleophile to help shift your equilibrium to the right. You can also, if possible, remove your product alcohol. So all you've done is create a totally different ester. Let me highlight here in just a different color. This right here ends up being, after protonation, your leaving group, right? There it is. Same old, same old. You're going to get tetrahedral number 1, right? It's going to be, the intermediate will be protonated. You'll get in equilibrium with tetrahedral intermediate number 2, just like up here, which will be neutral, which will be in equilibrium with tetrahedral intermediate number 3. So if you want to go through the mechanism for the transesterification, follow the proposed mechanism for the hydrolysis reaction, see if you can get those 3 tetrahedral intermediates. All it takes is a little practice. This is just same old stuff, right? What's a little bit different, though, for the esters is we can do a hydrolysis reaction, but instead of doing it under acidic conditions, we're going to do it under basic conditions. So we're going to call this base promoted, not base catalyzed, just to be picky about the wording, because to be a catalyst, you not only have to change the mechanistic pathway and shrink down the activation energy, right? Lower the activation energy by altering the mechanistic pathway. This is from kinetics, right? From Gen Chem. But you also have to come back again at the end of the reaction. We have to be able to capture you again at the end of the reaction. And under basic conditions, we're using the base as a nucleophile, so it gets kind of eaten up. So let's do a little generic reaction here. We're going to hydrolyze or crack the ester. We'll just use this. We're going to use hydroxide as not just the base, but also the nucleophile. So we don't need to protonate the carbonyl because hydroxide is a better nucleophile than water, right? It's negatively charged. That carbon is electrophilic. It's electron deficient. We're going to attack it and push electron density up through the carbonyl. Because this is an acid-base type of a thing, this will be in equilibrium with our first tetrahedral intermediate. And look, we're under basic conditions, so nothing is protonated. We have something that is either neutral or negatively charged, remember? Under acidic conditions, you have stuff that's either positively charged or neutral. Under basic conditions, you have something that's either negatively charged or neutral. So here, our first tetrahedral intermediate is going to collapse, and we're going to kick off methoxide. I'll explain in a second. You're probably like, wait a minute, because methoxide is a strong base. So is hydroxide, right? So either one is likely to be kicked off. We will talk about that. We end up with our carbonyl back again. And I'm going to draw this just a little bit more suggestively because obviously we're going to be taking that hydrogen away. We have kicked off methoxide, right? Very quickly, it's going to deprotonate your carboxylic acid. And you'll get, remember, under basic conditions, things are either negatively charged or neutral. Under acidic conditions, things are either positively charged or neutral. Under basic conditions, you can't get a carboxylic acid. You can get the carboxylate anion and an alcohol here. So let's just, in a different color here, explain what's going on. Your hydroxide is going to attack your carbonyl. So your hydroxide is the nucleophile. You're going to, and the hydroxide is a better nucleophile than water, so we didn't have to protonate the carbonyl oxygen of the ester. If you did, right, you wouldn't have hydroxide in the solution, right? You'd have water. So we're doing this purely under basic conditions. We're going to form a negatively charged tetrahedral intermediate. So two potential leaving groups in this situation are OH minus, right, hydroxide, or CH3O minus, methoxide. And they have an equal chance of leaving, right? Methanol and water have pretty similar pKa values, right? So I've chosen to get rid of methoxide because, again, this is the reaction that we're promoting. So either way, either group has equal chance of taking off. Your final products cannot be the carboxylic acid and methoxide, right? The methoxide ion, because if only one base is going to be protonated, it's going to be the stronger one. So you have a choice. You could have the carboxylic acid and the methoxide ion, or you could have the carboxylate ion and methanol. The carboxylate ion is going to be a weaker base than the methoxide ion because we can delocalize those electrons up into the carbonyl, right? Unlike under acidic conditions, this reaction is not reversible. Did you notice that up here, all of these steps are reversible? We have those equilibrium arrows after every single step. In a base promoted cracking of an ester here, reaction of an ester, this reaction is irreversible because the carboxylate ion cannot be approached by a nucleophile. So that's probably something I should highlight here. Notice the arrows are different here. Unlike under acidic conditions, this cannot be attacked by a nucleophile. It's negatively charged. In the acid catalyzed process, you make a carboxylic acid. You can attack that with a nucleophile. So that step, that last step, if the alcohol is hanging around, right? And you didn't really use an excess of water, it is totally possible, and if you're heating this up, probably will happen with acid laying around, that you're going to go backwards and form the ester again. But under basic conditions, hydroxide attacks your carbonyl carbon, right? You form your negatively charged tetrahedral intermediate. You're going to, which is unstable. It's going to reform, so your pi bond is going to reform, and you're going to kick off either methoxide or hydroxide, right? If you kick off hydroxide, then no reaction has happened. If you kick off methoxide, an equal chance of either of those happening, right? But if you do kick off the methoxide or the alkoxide, in this case it's just methoxide, could be any alkoxide, that leaves, then that's going to be a stronger base than the carboxylate ion. So that base will deprotonate your product carboxylic acid, and very quickly you'll form the carboxylate ion, which, because it's negatively charged, cannot be attacked by the methanol or whatever alcohol you've kicked off. And so that's the end of the road there. Under basic conditions, you're getting the carboxylate ion and some kind of alcohol. So that is how esters react. In the next video, we're going to run through reactions of carboxylic acids, and it's going to look pretty similar to reactions with esters. There's a new piece of functionality, though, and it's why I'm doing a separate video for the carboxylic acids. We're going to also introduce something called an acid anhydride. And so we'll run through some reactions with carboxylic acids.